Hi, NA Physics, it's Mr. Neff. Today I want to do the relationship between linear and angular momentum. But before we do you know what kind of birds like to stick together? I'll tell you about them at the end of the video. So I'd like to talk about the angular momentum of an object moving in a straight line. Let me get myself out of the way so you can see that. The angular momentum of an object moving in a straight line. Now you might say, what? What do you mean, angular momentum of an object moving in a straight line? Angular momentum is for something that's spinning. I totally agree, but consider this. Say you had a ball, clay, or whatever, and you take that thing and you throw it at the end of a stick. Now let's assume that that stick is fixed at this point right here. Well, whenever that ball collides with the stick, you know, what's going to happen? Well, you don't have to wonder. I think you know, but you don't have to wonder. We have a simulator for that. Now, our friends over at OPhysics, they have this simulator, and I think you should go and check it out on your private time. But under rotation, they have the angular momentum collision. Really good. And so this answers the question for us. So here's what they have. So there's this ball, and I can take this thing and I can make it so that it's, well, let's say it's moving as close to perpendicular to that rod as I can get it. Okay. Now, you know what's going to happen. Whenever I allow this thing to collide, it's going to collide. And now in this simulator, the ball sticks onto the rod. And in my example before, I said it was a ball clay, so it probably would not have. Regardless, what you saw after the collision was angular momentum. No question about that. So that if you believe in conservation of angular momentum, then that means that there must have been angular momentum before the collision too. Otherwise, it was just created somehow. And I don't believe in that. That, mind you, what I'm talking about is a function of the system. So this ball is going to slow down some because there's an external force on it. It's going to encounter a force from the end of the stick that pushes it to the left, and that's going to slow it down. The stick is going to experience an external force to the right, and it's going to speed up. But I'm talking about the system. So if the system at the end has angular momentum, then it must have had angular momentum beforehand too. You can see gravity's in play here too, but we're only talking about sort of right before the collision and right after the collision, kind of like that. Now check something out. Over here on the side, they allow you to calculate, or they calculate for you, I should say, the angular momentum of the ball initial. So that's another reason to think, well, maybe there is something to there being angular momentum here. I was able to set the mass of the ball to 2. The velocity of the ball is 2.2, and that's going to stay that way. I can't control that. But you can see that the initial momentum, linear momentum of the ball is 2 times 2.2 or 4.4. But here they have the angular momentum like it's 4.4 as well. There's a little bit more to it, but it's basically the same thing. And you think, well, does that mean angular momentum and linear momentum are the same? Turns out, no, they are not. But there is a quote-unquote conversion between the two. Back over to our slides. So angular momentum can be calculated as a function of the linear momentum. It is a cross product, but it is still a function of it. So you see what I have over here. I have angular momentum as a vector is equal to the radius vector cross the momentum vector. And so what we had there is we have our momentum vector P. So this vector probably was the velocity, but it could serve as our linear momentum vector too. And then we have our R. Now, you could draw straight down here like so, and then if you did that, then you would have to say, well, cross, and so the part of this that you'd be interested in would be this part right here. You know what I'm going to do is I'm just going to help us out, and I'm going to just say, hey, that's the R vector that we're interested in, kind of like the lever arm when you're calculating torque. And so you see, I'm going to take these two and I'm going to multiply those together. So I'm not really as interested in this distance right here. I'm going to get rid of that. I'm interested in the perpendicular distance between the pivot point down to the line that the momentum is acting on. I don't really want to call it a line of action, but it's a lot like that. Okay? So I have a quick example here, and the example shows some joggers, and the joggers are, well, they're running linearly. And so a second ago, you may have thought, well, it's silly to ask about their angular momentum. If they're not running around a circle track or something, then what angular momentum could they have? But now we see that there is an angular momentum about a pivot point or about any point that does not go through the line of action. So here's jogger 1 right here. And it says that the jogger 1 has a mass of 65 kilograms and runs in a straight line with a speed of 3.35 meters per second. We ask, what is the magnitude of the jogger's linear momentum? Go ahead and calculate that real quick. Stop the video and calculate that real quick. Okay, you can see what I've done here. I took the momentum as the mass times the velocity. So I took the two given numbers, the mass and the velocity. Careful, velocity is a vector, so you want to have the direction on there too. And I'm going to get the linear momentum. 3 significant figures on that, and the direction that was on the velocity is the direction that's on the momentum. Now, part B says, what is the magnitude of the jogger's angular momentum with respect to the origin? So you see where jogger 1 is, and these don't line up perfectly, but jogger 1 is at a point that we're going to call 8, 5, 8 over and 5 up. Again, I know they don't line up perfectly, but that's what we're going with. I'd like to know about this origin right here. I'd like to know what is the angular momentum. Please stop the video and give that a shot. See what I've done here? So angular momentum is r vector cross the linear momentum. So the perpendicular part of the r vector, remember the real r vector is going to go out to there, but this is the perpendicular part, and that's the part that we want. So that's 5 meters long. 5 meters times the angular momentum times the linear momentum is going to give us the angular momentum. So 5 times 218 is this number, 3 significant figures on that. Hey, notice too, the 2 different kinds of momentum do not have the same unit. The unit on linear momentum, kilogram meter per second, like you're used to, times a meter is going to be kilogram meter square per second for the angular. The direction on the linear momentum just points the same as the velocity, but since this is a cross product, it points perpendicular to the plane of the other 2 vectors. Hey, use the right-hand rule, pause the video, and try to decide which way this points. So if we're doing R cross P, it might be helpful, at least in your mind, or maybe really, to draw it like this. So here's my R, tail to tail with my P. Now take the thumb of your right hand and put it in the R direction. Take the finger of your right hand and put it in the P direction, and now your fingers are pointing down into the ground. And so we'll say this is down into the ground. All right, I hope you learned a lot about the relationship between linear and angular momentum. And what kind of birds like to stick together? Velcros. See you next time.